So for the first question, we had a comparator, and I explained what the comparator did. The comparator simply compares two voltages. Ethan, you with me there? The comparator's got two inputs and one output, and here each input is connected to a different point in the circuit. So I've got one voltage divider, which when the switch is closed, how much voltage will I get at this point here, Leigh? 5 volts, fantastic. Plus 5 volts. And when the switch is closed, how much, Anthony, will I get at this point here? Exactly at the minute the switch is closed. I beg your pardon, 2.5. My mistake, 2.5 volts, good. So what about here though, Anthony? How much voltage will I get the minute the switch is closed? Someone else? Tash, what do you think? Switch closed, this point here, connected over here. I've got a meter measuring voltage going to ground. It's a voltmeter. What's it going to measure between here and ground? Paul? Not 2.5. Good try, but I used the word instantaneously. Chris? Not 5 volts. 0. Why 0?
What's the voltage across the capacitor the moment the switch is charged?
Yeah. Yeah. Listen to what James is saying. Think about that capacitor charging curve. So we've got the capacitor charging voltage, or the capacitor voltage under charge, and we've got the capacitor charging current coming back the other way. So at instantaneous, this is switch on. The moment of switch on, I've got absolutely 0 volts. This is voltage across the capacitor plates, and I've got current maximum. And the current there, you could work out, it'd be 5 volts divided by 1K, 5 milliamps. And then that current is going to rapidly decline, 1 time constant, 2 time constants, 3 time constants. All right, but the voltage isn't going to reach the peak until 5 time constants later. So at the moment of switch on, we actually end up with 0 volts at that point there. And then this is going to slowly charge based on the RC time constant between the 1K and the 10 microfarads. Just out of curiosity, how much would that be? What would the time constant there be? Grab your calculators, work it out. 1K, 10 microfarad. 1 time constant equals, is it 10 milliseconds? 1K times 10 microfarads, 10 milliseconds. So that 10 milliseconds is not how long it takes for the capacitor to charge up completely. Don't fall for that. It's how long it takes for 1 time constant of the charging. So 1 time constant, that's going to take 10 milliseconds. 2 time constants, 20 milliseconds. 3 time constants, 30 milliseconds. And we've got a bit further to run. But in fact, at 3 time constants, we're about 86% of the way there anyway. So some people say that's getting pretty close to fully charged. The question went on to say, after how many time constants will the comparator change its output state after the switch is closed? Well, what this is doing, it's looking at the voltage here, and it's saying when this voltage here slightly gets higher than that, by just a tiny fraction, the output here is going to toggle, it's going to flip. So in other words, how long will it take for this voltage here to reach 2.5 volts? Well, what's 1 time constant in percentage? Dave? Not 68, 63%. 63%. So after one time constant, the voltage on the capacitor has reached 63% of its possible maximum charge value, which is 5 volts. 63% of 5 volts is going to be more than 2.5 volts. It's going to be about 3.3 volts. So that's going to well and truly exceed. We've gone past where the question's asking us for. The question again is saying, how many time constants will a comparator change its output state when the switch is closed? And the answers are 1.5, A is 1.5 time constants, B equals 0.7 time constant, C equals 1 time constant, and D, and I think a lot of people went for D, it must have looked good, 2.0 time constants. Well, we know that 1 time constant is 63%. Get your calculator out. What's 63% of 5 volts? 3.15 volts. Bang, it's already way past the 2.5. We want to know what percentage of a time constant we're looking at for 2.5 volts. You can see this if you get your universal time constant chart and you just look along and say, there's about a halfway, there's 50%. That's going to be around about 0.7 of 1 time constant. Bang, there it was there. Comments? Ethan, you look totally puzzled at that. Did you get it right or wrong? Got it wrong? Can you get it right next time? Possibly. James, any comments? Oh, what's the voltage here after 5 time constants?
So that they realise there's a transition on that leg. So it goes from 0 to something else.
Well, yeah, it starts at 0 volts. We said it starts at 0. But what does it reach after 5 time constants? Yeah, that's a good question. Lachlan? 5 volts. Has to be 5 volts. 0 to 5 volts. That's right. So the charging current started off high and dropped down to 0 at 5 time constants, and as the charging current dropped down to 0, the charging voltage reached the maximum. You think about this, probably a good way to explain it is if you've got a battery in the circuit and you've got a meter here measuring current, and there's your capacitor, and you've just closed the switch. Bang, you've just closed the switch, you've held it down. The current's going to be maximum while it's charging. And then once this is fully charged and it reaches the full 5 volts that we had there, 5 volts, 5 volts, we've got the same potential there as what we've got there. When we've got equal potential on both sides of the current meter, how much current is flowing? 0, exactly. So that's why the current drops down like that as it charges to fall back down to 0, and that's why the charge is maximum when the current drops down to the bottom. Any other questions about that? It's a fairly important question. All right. The next question was about 3 capacitors in parallel. I don't think we need to spend too much time on this. 100 microfarads, 15 microfarads, 3.3 microfarads. Question was simply, again, a multiple choice. The total capacitance is 20 microfarads, 2.13 microfarads, 3.3 or 28.3. Caps in parallel, we simply add them together to get the total capacitance. 10 microfarad, sorry. So 10, 25, 28.3. So that should have been, if you know capacitance and you've read this stuff, that should be like a 5-second answer, which is great for a multiple choice question worth 1 mark. So easy, once you know how to do it. Any questions about capacitors in parallel? Next question, a little bit more difficult. Oops. "24-volt supply, 1K, 4K7, 5K6, 2K2, and then we had a system with 2 resistors across here, and we had a switch, and it said that the switch was depressed. So once that switch has been depressed, and again, depressed, pressed means the same thing. That means that we've got a short circuit across that. Therefore, we can ignore it. I don't even need to write the value next to it. We've got 1.2K there, 1K2. So the circuit works out that we've got 12.5K, these add up to, in parallel with 1K, or 1.2K, 1K2, this one here, and then added to the 1K, because we've got this 1K up here, and that's going to be the total resistance in the circuit. So 12.5K in parallel with 1.2K. Look, at a guess, I'd say that's about 900 ohms. 900 ohms plus 1K, about 1900 ohms. And then the question is asking us, what's the current going to be in the 1.2K resistor? So we need to find out the total circuit current. REQ for the whole circuit now is 1900 ohms. IT is going to be 24 divided by 1900, and it's going to be equal to, again, I've used an approximation there, I might be out by a bit. About 12.6 milliamps. And the answers that I had there were 1.15, 10.45, 4.10 and 3.35. So if the answers had been too close together, I would have had to get my calculator and work that out more correctly, because I'm probably wrong with that 900. But just looking at that, I approximated 12.6, and I've got an answer here of 10.45, which was B, so I'm going to go with that. Let's, did somebody work out with their calculator what is 12.5 in parallel with 1.2? 1.1K, all right. I'm too low there. That should have been about 1.1K, bad on the day. But, although I'm out by a bit, I'm out by 10%, I'm still I'm still okay with a multiple choice question to make a guess at that answer and come up with a ballpark figure and get it right. You can save time, and then the idea is if you've got that time up your sleeve, you finish the test, you can go back through and put an asterisk next to it and then go back through with the calculator and do it properly in case you didn't get it quite right the first time. Any other questions about that? Look, just while I've got it there then, before we go on, let's just do some more work on this because I think this type of question is quite important to us. Because once it's gone off the board, it's gone for good. So we said 1.09K, was it, Dave? Yeah? 1.09K. That means that IT is going to be 1.09 plus 1K, 2.09K, 24 volts divided by 2.09K equals, did somebody do that? 11.48 milliamps. Okay, so in fact those answers on the page, there was nothing that was correct anyway. Because that answer B was 10.45. I beg your pardon, that was through the second resistor, wasn't it? That's the total current. And then we had to break that down into a current divider, didn't we? So that REQ value there, REQ of this whole network works out to be 1.09K. And then we want to find the current going down through the 1K2. So that would be divided by the 1K2 and then times the total circuit current of 11.48 milliamps. So we actually didn't do that the first time I ran the question. 11.48 milliamps. And then when we do that, do we come up with exactly 10.45? $10.45 milliamps. So that's what's coming down through here then. 10.45 milliamps. What about what's coming down through this branch here? I mean, yeah, is there an easy way to do that? Do we have to go through the whole rigmarole again to get that current? Just subtract it because we've got the, yeah, exactly. We've got the total current, which was 11.48 milliamps. That's here. And then if we subtract the 10.45 milliamps from it, that gives us the current going down through there, which was how much? 1.03. And the 1.03 milliamps plus 10.45 milliamps has to then add up to be equal to the 11.48 milliamps, which is feeding that parallel network there. And I'm glad I went back into that question because I'd actually, again, nobody caught me on it. I didn't break it down the first time and go through and actually do the current divider. I was only working with the total current. Yeah, all right. Next question. We saw a question like this last week. Voltmeter. and we had some other resistors here. In fact, 2 in parallel, junction, 1 down to ground, 270 ohms, 480 times 2. When we've got 480 ohms in parallel, very easy to work out the total. 2 identical value resistors, divide it by 2. So that network there comes down to be 240 ohms. This was 12K, 10K, and the applied voltage was 24 volts. 10K, to work out the voltage here, let's call that A, VA, let's call that VB. The whole question was based on solving what the voltage is on the meter. It was multiple choice. We were given 4 answers, but we're just going to have to run with this and work it out. So it'll be 10 divided by 22. You don't have to put the K, it's all in K, so it's just a ratio. 10 divided by 22, R2 divided by R1 plus R2, times V applied, 24, equals 10.9 volts. Agreed? Anthony? Good? You're just going to run with it. Voltage B. Did somebody work out voltage B? Yeah, 10.909, 10.9, James, for the rest of us. For voltage B, VB, how do we do that? Think about it. R2, R1, R2 divided by R1 plus R2 times VS. Very good. You love voltage dividers, James, I know that. You should be home and hosed with this. So what do we end up with? 270 divided by divided by 240 plus 270, which is 510 times 24. And James, how much did you get? 12.7. Forget the 0.6, we don't need that. Oh, look, yeah, you're right. If an examiner had written this with answers that were all within 10 millivolts, I fully agree, you'd have no choice. You'd have to do that, yeah. So this has to be then VB minus VA, or if VA was bigger than that, you know. In this case, I've chosen VB because it was bigger, 12.7. I just want to make a net result which is positive. So that'll be 12.7 minus 10.9. And that equaled 1796 millivolts. 1.79 volts. Again, make sure you learn how to do this. It's basically derived from the Wheatstone bridge work that we did, and looking at 2 voltages, and again, it's not too much different to the comparator question we had in question number one. Comparing the voltage there with the voltage there. In this case, though, we're just comparing it with a voltmeter instead of using that little triangular comparator device, which was looking for any difference between them. Any questions about that? .27 volts. Question 5. Resistor, 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 ground. VB, VA equals, and wow, 4,700 ohms, 4,700 ohms, 4,700 ohms. 1/3, 1/3, 1/3, 27 divided by 3 equals 9, 9, 18, 27. That was a gift. It really was. Yeah, poor Ethan. You had it upside down. Oh no, how'd you do that? All right, let's have a think about this. Say they were not, say on the day the examiner had not been so easy with you guys, and say he had made these different values. Let's put some different values in and see how we'd go about working it out, because here it was just so easy. I just went, 3 identical value resistors, 1/3, 2/3, the whole amount. Let's change the values. Now you're absolutely correct in saying that too, because maybe the question should have said VA with respect to ground. How did you work the other way? So you mean you went between there and there? Oh, to give you 9 volts, VB. And then the next one to there would of course be 18 volts. Look, to be fair, I can see your point. But how many times in labs so far this term have we put the negative terminal of the voltmeter, say, on the rail and then measured down the circuit that way? We've always gone from ground and measured up. But to be fair, point taken, it should have said VA with respect to ground and VB again with respect to ground. Yeah, point taken. It's a good point. Any other comments about that? Okay. No, it's a good point. So let's put some values. Let's make this 5K6, 7K2, 3K3. All right, let's find the voltages. How do we go about it? Where do we start? All right, what's the REQ? Wow, that was quick. 16.1K. Geez. REQ. 16.1K. All right, then what do we do? It's a voltage divider, so I'd probably tend to start from the bottom. I like to think about that R2 over R1 plus R2 times VS. This is James's favourite equation. And then I would be, with a different colour, I'd be lumping those together. Hang on, James, you can kill him afterwards. You're not going to do that. I'd be putting a circle around there, and remember, I've got to get R1. I know what R2 is. R2, I'm calling that 3.3K, but R1, I need to add those two together. So what's that going to be? 12.8K. Yeah? I'm only interested in working out this point here, first of all.
Yeah, but that's what I'm saying. You have to then deduct that from 27. That's what
The way he was doing it.
Yeah,
Yeah, the way he was going to do it. Well, look, just Tiger, just hang off, just stand down for a minute and let's just go with this. So, can we plug these values in then? 3.3K. So, this will be for VA, will be equal to 3K3 divided by 12K8 plus 3K3 times 27. So we really, here when we look at the equation R1, R2, we've broken it down, but did we need to do that? Because by the time you add R1 and R2, you've just got the whole network, and the whole network we already knew was 16.1K. So that's 3K3 divided by 16.1K times 27. Thank you, David. You're on the ball. 5.53 volts. And that again is VA. 5.53. VB. VB again is equal to R2 over R1 plus R2 times VS. But in this case, R2 is going to be this, divided by the whole lot. I've got to, because I'm stepping up to come to that point, so everything below that point is going to now be my R2. So it'll be 7K2, 10K5. 10K5 divided by 16.1K times 27. 10,500 divided by 16,100 times 27. 17.6 volts. .53 volts for VA, 17.6 volts. With respect to ground, as Lachlan said, that should really be, with respect to ground. Of course, with respect to the rail voltage, different again. Any comments about that question, other than the ones that we've already had? Voltage dividers, we did them many weeks ago. They're quite important, and there's the secret to your success. R2 divided by R1 plus R2 times VS. Just remember though, if you're working there, everything below there is going to be R2, and everything above there is going to be R1. Okay to take that off? I think this is really good revision for your test, which is sort of right in front of us next week. Just looking at the time, this is probably going to take us up to lunch, and I don't mind doing that because revision is pretty important at this stage of the game. And then we can do our practical stuff after lunch. Question 6 had a 5-volt battery. $1K, 10 microfarads, plus minus, and it said after a capacitor has charged for 1 TC, so 1 TC is going to be 63% change, and that change could be 63% change in the voltage increasing or 63% change in the current decreasing. The current, don't forget, decreases by 63% and the voltage increases by 63% in one time constant. After the capacitor has charged for one time constant, the percentage of current instantaneously flowing in the resistor is 63.2, 36.8, 13.5, 5.4. Well, guess what? We're back to our I, V, one time constant, we're down to 36.8% of the current. The answer was B. The current hasn't dropped by 36%. The current has dropped by 63%, which leaves only 36.8% left in the circuit. All okay with that? Who got that one right? Okay, about half the class. All right, that's pretty good. You've got a good understanding then of your chart. So that chart's super handy to us, and of course you've got that chart available in your tests and your quizzes, so don't hesitate to use it, especially when you're learning this stuff. Oh, it's the same drawing, is it? Yeah, good point. Next question said, as the capacitor is being charged, the current flowing into the capacitor... Oh, this was a gift question. I almost took this question out of the quiz, actually. I looked at it last night and I went, oh, am I feeling generous? Yeah, I'm feeling generous. As a capacitor is being charged, the current flowing into the cappy increases, decreases, stays the same, or stops after 66%. The answer was obviously D, stops after 66%. No, it wasn't. I'm only kidding. Don't look so serious. The current flowing into the capacitor decreases. It decreases for 5 time constants, where it gets down to zip, 0. So the answer was B. Unfortunately, I know only a couple of people in the class got that one right. I don't know why. I thought last night when I looked at the quiz, I thought they'll all get that one right. And I marked it and I went, well, I was wrong again. All right, question 8's a bit different. You read that one right? It was the one above that you got wrong, was it? Yeah, I don't know how you got that one wrong, James. Alright, so this one just... We've got a circuit with 5 volts being applied via a 1k ohm resistor to limit the current via charging to the 3 capacitors. The capacitors were rated at 470 nanofarad, 330 nanofarad, and 100 nanofarad. And the question said, what's the total capacitance? So the first question was CT equals, and you'd have to go 1 on the 470 plus 1 on the 330 plus 1 on the 100 and nanofarad, of course. And then 1 on the whole lot, the sum of the reciprocals, same as for parallel resistors, as we've already seen. And that worked out to be 65.97. And as we saw in our theory earlier, the new CEQ, the new equivalent capacitance in this type of circuit, is always going to be smaller than the smallest capacitor in the series string. 100 nanofarads, new answer, 65.9 nanofarads. So if you do that sort of question in a test and you come up with some crazy answer like 171 nanofarads and you write that down, you're not doing yourself any favours, because you should be going 171 nanofarads, I've got it, so easy. You should be looking at that saying, oops, can't be right. I've got 100 nanofarads. I've made a mistake. So just think about what you're doing there. The charge and voltage on the middle capacitor is, on the middle capacitor, different coloured crayon. All right, charge, Q equals C times V. And that's going to be CT. CT times VT. So we're going to have the 65.97 nanofarads times 5 volts. Do not look at that 1K resistor and go, oh, I got 5 volts, but I've got 1K. I must have some weird voltage divider. How do I do that? No. The resistor is only providing a time constant variable in the circuit and just delaying how long it takes for the capacitor voltages to all reach the 5 volts. Doesn't have anything to do with working this out. So we run the maths on that and we get a charge of 330 nanocoulombs. Spell that right out, nanocoulombs. It's a lot of electrons. And then, because we have to, well, the charge on each capacitor in a series circuit, the charge is the same. Charge, same on each cappy. So the first part of the answer is 330 nanocoulombs. But then it said, what's the voltage going to be across this capacitor? Voltage? Question mark. Well, we've got to rearrange that equation to make V the subject. V equals Q on C. And that's going to be the total charge, 330 nanocoulombs, divided by 330 nanofarads, and that equaled, well, look, I've written down 999 millivolts. I guess you'd round that off at about 1 volt. 1 volt developed across that. And look, if you're not sure about this, run the maths on the first one. Let's just do it anyway. Grab your calculators, run the maths, tell me what the voltage is on him, and tell me what the voltage is on him. Because this all comes too quickly. $700 millivolts across this, 701 millivolts. $3.3 volts. Yeah, 1 volt, which I already did over here, 1 volt. So, if I add those together, Chris, if I add these together, 701 millivolts plus 1 volt plus 3.3 volts, what do I get? The voltage source, the voltage supply, exactly. They have to all add up. It's just like a series resistor circuit. The voltage drops have to all add up to the supply voltage. Yeah, exactly. So if you're in doubt in an exam about whether you've done that right, just apply the same methodology that you've used to work one out to him, and if they don't add up to the whole lot, then you can probably say, oh, you don't know what you're doing and you should just go home and slash your wrist or something like that. I don't know. Yeah, it is. All right, last question. Yeah, we'll take all the razor blades off you on the day, James. The last question was, we start to throw some of these devices in, and this is just an integrated circuit that I explained before you did your quiz, and it's got various terminals around it, but it's got one here which is called just for trigger, and that point there is connected into a voltage divider. And the voltage divider had yet another one of these tongue depressor things across it. because the question said switch 1 is depressed. So it obviously needs some Prozac or something like that to make it underpressed, I don't know. Switch 1 is depressed, so therefore that is a short circuit across that. Short circuit. We don't even need to know the value of it. We've got plus 5 volts. We do need to know the values of the others. 1K, 1K. This question really went in the same basket as question 7. I looked at this and I said, gee, this is a gift of a question. With the push button switch depressed, the voltage at pin trigger on the integrated circuit will be pin trigger depressed, 1K, 1K, 5 volt, plus 2.5 volts. Comments? It's only a voltage divider, people, that's all it is. If the switch had not been depressed and been open, how much would we have had at that point there? Let me see, that was also 1K. If we take away that short circuit and we open the switch, what new voltage would I get at this point now? Tash? 1.6? Why 1.6? 3 identical value resistors. How clever. 1, 1, 1, 1/3, 2/3, full voltage, 1/3 times 5 volts equals 1.66 volts. Love it. And that's our last quiz. Done. Next week it's the test.